All right, so for each year t, the population of a forest of trees is represented by the function a of t equals 115 times the 1.025 raised to the t power. Now, in a neighboring forest, the population of the same type of tree is represented by the function b of t, which is 82 times 1.029 to the t. Now, what we want to do is round answers to the nearest whole number, and it says which forest population is growing at a faster rate. Well, all we have to look at is our b value. And which b value is larger? Well, this is 1.025. This one is 1.029. This one is larger. So we get b of t is going to be the one growing at a faster rate because 1.029 is greater than 1.025. Now, which forest had a greater number of trees initially? Well, A is what we have there. Well, here we had 115. Here we had 82. So A of T is the one that's greater because 115 is greater than 82. So that was pretty easy. All right, well, let's go to the next one. Assuming the population growth models continue to represent the growth of the forest, which forest will have a greater number of trees after 20 years and by how many? Okay, well, that one we have to plug in 20. So A of 20 and B of 20. So our first one was 115 times 1.025 to the 20, and this one was 82 times 1.029 to the 20. And it's going to give us, now this is where we have to round to that nearest whole number, I believe. So let's go over here and get our values. So we had 115 times 1.025 to the 20 and arrow down in parentheses. So we get 188.44, and so we'll round that to 188. And then our other one was 82 times 1.029 to the 20 and parenthesis, and we get 145.25, so 145. Now let's go ahead and do our subtraction here in case we don't want to do a subtraction later. And so we get 43. So those are all the values we need. So let's write them down. So the first one was 188.44, and so that's approximately 188 trees. And this one was 145.25, if I remember right, and so that's going to give us approximately 145 trees. So the difference was equal to 43 trees, and so there were 43 more trees in A of T. Okay, so there are more trees in A of T forest. Okay. Now, assuming the population growth models continue to represent the forest growth, which forest has a greater number after 100 years? Well, now we do A of 100 and B of 100. And so 115, 1.025, 100. This is 82, 1.029, 100. And so we're going to do the same thing, except we're going to plug in our 100. So guess what we're going to do? We're going to go back so we don't have to type everything over. And so this one, we're going to plug in 100 and we'll get a value. So 1358.58. Okay. And then we'll go back again to that. We'll plug in our 100. Might have been easier just to type it in, but that's okay. So we have 1430.05. So if we round to the nearest tree, that's going to be 1359, and that's going to be 1430. So we'll take 1430 minus 1359. So that's going to be 71 trees. So let's write all those down. This was 1358.777 or approximately 1359. And this one was 1430.050. And so that was 1430. And our difference was 71 trees more in the B of T forest, okay? Whatever it was, says B of T, okay? So B of T was larger by 71 trees when we went to that 100. So that's where it shows that that growth is larger, so it's going to be slower, kind of at the beginning, but eventually all of a sudden it's just going to go boom and take off, whereas the other one's just going to still grow gradually and not go as quickly, okay? All right, let's just go ahead and go on here. All right, so if a car was valued at 38,000 in the year 2000, by 2013 the value depreciated to 11,000. If the car's value continues to drop by the same percentage, what will it be worth in 2017? Well, I think what we're going to have to do is we're going to have to say, well, this is times 0, and so this is our initial value. So that's going to give us a point 0.038,000. And then by 2013, that's 6 years later, so that's 6, and it's going to be down to 11,000. So that gives us those 2 points. Now, can we find a function? Yeah, well, let's do 11,000. Now this is our a value, so equals 38,000 times b to the 6. We're just going to use the b function this time. So that was nice. That was a. This is our, x and y based on that a function. Now we'll divide by 38,000. So b to the 6 is, that was 11,000. I put 10. Oops. It's like, wait a minute, something doesn't look good. All right, so that was 11,000. So 11,000 divided by 38,000. And so we're going to have to take that to the 1/6. So we'll take that to the 1/6. So b is equal to 11,000 divided by 38,000. So let's clear that. So 11,000 divided by 38,000. And we'll get a value, and we'll take that to the 1 divided by 6. So I'm just taking that answer and raising it to that power, and I get the 0.8133326. So that was going to give me the 0.81333, and we'll leave it at that way. It's far enough. And so now I can plug that into my original function, which is going to be a of t equals my a, which is 38,000, times b, which is 0.81333, to the t. And now I want it in 2017. Excuse me. So that's 10 years later. So 38,000 times 0.81333 to the 10. And so now I have 38,000 times 0.8133 and 3 to the 10, and I get $4,813.40. So it's going to give me 48,113.40. Okay. And again, depending on how many decimal places you used here, you'll get different values for your decimal places here. All right. What about this one? An investment account with an annual interest rate of 7%, so that's going to be R equals 0.07, was opened with an initial deposit of 4,000, so that's our P. Compare the values of the account after 9 years, so that's our T, when the interest is compounded annually. Well, that's N equals 1, 4, 12, and that's PERT. Okay. All right, so 1, A of 9, 9 years, 9 equals, now we have 4,000 times 1 plus 0.07 over, we'll do our first one, which is 1, then 1 times 9. We'll find that value. And then we'll have 2, we'll have A of 9 is equal to 4,000 times 1 plus 0.07 over 4 to the 4 times 9. And then we'll have A of 9 equals 1000 times 1 plus 0.07 over monthly is 12 times 12 times 9. And then the last one, 4, that's going to be a of 9 equals p e to the 0.07 times 9. Okay, so let's go get those values. Let's clear that out. So we have 4,000 times 1 plus 0.0, well, that would technically work, but 1 plus 0.07 divided by, and that first one was 1. Then we're going to raise that to the 1 times 9. Maybe let's do 9 times 1. That way we can change the other one easier. Okay, so we get 7353.84. Then let's do that again. And so now we're going to divide by, now let's insert, and oh, we don't have to insert, well, it's just going to be 4. And then this is going to be a 4 out here. So 74, 69, 63. And then we'll do it again. Now we'll have to insert because we're going to go do 12. So it's going to be 1, 2, and 1, 2. So 7496.71. Now notice every time we compound more often, we get more money. And now the most we can ever get would be the continuously compounding with everything else kept the same. And so it's going to be 4,000 e to the 0.07 times 9. And so this would be the most, 7510.44. So let's write all those down. And the first one was 7353.84. The next one was 7469.63. The next one was 7496.71. And our last one was 7510.44. So you can see as n increases, we get more and more money until we hit that continuously compounding interest there. Okay. All right, so that's all I have. So hopefully that will help you.